When you perform a Google search, how does the browser determine the relevance of the results based on what you typed? The foundation of Google search begins with PageRank, or PR for short, and it is arguably the most important algorithm used by Google up to this date. PageRank is an algorithm that estimates the relevance or importance of a website. But how do we define relevance? The relevance in the PageRank algorithm describes a common link between web pages. So we can say that PageRank works by counting the number of links that a web page has to determine the rough estimate of how important that web page is. However, this is not enough by itself, since it would be easy for a web page to have many subpages that link to the main page, or some artificial pages whose purpose is to link to a single page. Therefore, one could in theory make their website as relevant as they want. This is why we expand the definition of our algorithm to fix this issue, by stating that the relevance of a web page is based on the amount of links from other relevant pages that that website has. But now, how do we calculate the importance of a website if by doing so we would need the importance of other sites? This is where we introduce the random surfing model, or random surfer model. The random surfing model is a graph model which describes the probability of a random user visiting a web page. So, let's take a look at the following example. Imagine a random user browsing any randomly selected website. Then, they choose a random link inside that page to another page. Next, they repeat this process in the second page, picking a link at random and visiting the next website, keeping a count from 0 to n for the amount of times that the user visits each page. So, pages that have more links to them are more likely to be visited, and as a consequence, the pages that they link to are also more likely to be visited. After a set amount of time, we can determine the corresponding weight based on the total count for each page and the relative relevance to that page. So this one, the page number 4, is the most relevant page in this example. So we could say that the most relevant pages are those where we are most likely to find our random surfer. There is, however, another problem that arrives when trying to implement the algorithm that we explained so far. That is, the fact that pages are not all connected to each other. So if we randomly start on page 6, for example, after following the links for any length of time, no matter how big, we will never reach any other page outside of these 3 pages. It is necessary then to reset the random page in which the surfer is by utilizing something called a damping factor. But what is this damping factor? Okay, so suppose the damping factor for our algorithm is 0.90. This means that there is a 90% probability of, at any time, a random link for the next page will be selected from the current page, and the other 10% of the time, a new random page from the internet will be selected. So the process starts all over again, so that eventually all pages are reachable no matter the arrangement of the set. So we can see that in the following example, we start at page 2, then follow up to page 1. But then the damping factor affects it so that a new random page is selected, in this case, page 7. Then, following the algorithm normally, we can see that another leap occurs and the new randomly selected page is page 3. So in time, every page on this graph can be reached no matter the arrangement of the set. We can see, as the previous example, that as before, the most relevant page in this graph is actually
This is how
page
we
4.
can explore
Once again, all parts of the network, and thus we can take any network arrangement of websites and determine the relative importance of each page in the network. But we must note that the first few iterations of the algorithm are not perfectly accurate. But by following the weak law of large numbers, we can infer that the algorithm approaches the expected result for a graph. When calculating PageRank, pages with no outbound links are assumed to link out to all other pages in the collection. Their PageRank scores are therefore divided evenly among all other pages, so that these random transitions are all added to all nodes in the web. This residual probability d is usually set to 0.85 or 0.90, estimated from the frequency that an average surfer uses his browser. So the equation is as follows. Where the function L of PI/PJ is the ratio between number of links outbound from page J to page I to the total number of outbound links to page J. The damping factor forms a stochastic matrix. A stochastic matrix is a square matrix used to describe the transitions of a markup chain, which is a random variable model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. The damping factor matrix is therefore a variant of the eigenvector centrality measure used commonly in the network analysis. Following the first simple example, the corresponding PageRank for each node is shown here, with A, B, C, and D being the nodes and the arrows representing the edges. We can see that C has the highest relevance in the graph and A has the lowest. We can also observe that although D has relatively few nodes linking to it, the fact that it is pointed by irrelevant nodes increases its own importance. PageRank has a time complexity of big O of n plus m, n and m being the number of nodes and the number of edges in the graph, respectively, and a space complexity of big O of n. With that said, I would like to end my presentation on this topic here. Thank you for your attention.